In 1903, I stood before the Swedish Academy to accept the Nobel Prize in Physics. The element I spent 4 years isolating, radium, was silently destroying my bone. The element I spent 4 years isolating, radium, was silently destroying my bone marrow even as the world celebrated our work. 8 years later, I would return to Stockholm alone, this time for the Nobel Prize in Chemistry. No one before me had won Nobel Prizes in 2 different sciences. But what killed me also revealed something far more disturbing than any personal fate. The atoms that make up your body are not permanent. They never were. Everything you believe about the stability of matter is wrong. Most people believe they understand radioactivity, but what they actually understand is a collection of associations, and those associations are almost entirely wrong. Danger, glowing green substances, nuclear disasters, mysterious poisons seeping out of rocks, that is what comes to mind, and none of it captures what radioactivity truly is. Henri Becquerel first noticed the phenomenon in 1896, but he did not understand what he had found. His photographic plates darkened near uranium salts, and he assumed some kind of phosphorescence was responsible, that sunlight had charged the uranium and it was slowly releasing that stored energy. I knew it was something far more fundamental. My measurements at the Sorbonne proved that the radiation continued undiminished whether the uranium sat in darkness or light, in heat or cold, for days or weeks or months. This was no phosphorescence. This was something inside the atom itself. The fundamental mistake almost everyone makes is treating radioactivity as something that happens to certain materials under certain conditions, like heat triggers melting or electricity causes sparks. That view has it completely backwards. Radioactivity is not something that happens to matter. It is what certain matter is at the atomic level. The intensity of radiation depends neither on chemical combination nor on external circumstances like light or temperature. The radiation exists constantly, spontaneously, without any cause of excitation whatsoever. 1/10 of a gram. That is what 4 years of labor produced. I possessed 1 decigram of very pure radium chloride after processing several tons of pitchblende through thousands of crystallizations and countless measurements. The shed where Pierre and I worked provided neither weatherproofing nor proper ventilation. Moving the containers, transferring the liquids, stirring for hours at a time with an iron bar in the boiling material inside cast iron basins, the labor was exhausting. But the demonstration that cost so much effort became the foundation for an entirely new branch of science. Producing radium in the pure metallic state required assistance from André Debierne and years of additional work until 1910. The method involved distilling under very pure hydrogen the amalgam of radium formed by the electrolysis of a chloride solution using a mercury cathode, and this established radium's status as an element once and for all. Skeptics had suggested radium might be uranium in some excited state, while others proposed that unknown forces acting on ordinary matter could explain the radioactivity. But isolating pure metallic radium collapsed every alternative explanation. The chemistry of radium holds its own surprise. Radium differs little from barium in chemical terms, since the salts of these 2 elements are isomorphic, and radium salts prove usually less soluble than barium salts. Strong radioactivity involves no chemical anomalies at all. The chemical properties match exactly what Dmitri Mendeleev's periodic table predicts, based on radium's atomic weight of approximately 226. The same periodic system that organized all known elements accommodated this new one perfectly, its radioactivity notwithstanding. Consider what this means when you look at a piece of uranium sitting on a table in complete darkness. No heat reaches it, no electrical current passes through it, no chemical reaction disturbs it. Yet at this very moment, and at every moment, this substance throws off energy into the surrounding space, whether anyone observes it or not, whether the room runs hot or cold, whether it sits in vacuum or air. The radiation continues year after year with a constancy that makes mockery of everything 19th century physics believed about energy. Systematic measurements using a precise electrometer with piezoelectric quartz allowed me to detect the ionization of air around uranium compounds, and what I found was remarkably clear. The amount of radiation corresponded exactly to the amount of uranium present, with double the uranium producing double the radiation, and half the uranium producing half the radiation. Chemical form made no difference whatsoever. Uranium metal, uranium oxide, uranium dissolved in acid, the radiation scaled precisely with the quantity of uranium atoms and nothing else. Chemical phenomena behave entirely differently. Chemical properties depend on bonds between atoms, on temperature, on the presence of other substances. But this radiation came from the atoms themselves, completely indifferent to their chemical surroundings. Every substance you have ever touched, every object you have ever seen, consists of atoms. The classical view that dominated chemistry for a century held that atoms were eternal and unchanging. A gold atom in an Egyptian pharaoh's crown was identical to a gold atom in your jewelry, and it had never changed, could never change, would never change. The atom represented the final, irreducible unit of matter. Every chemistry professor in Europe believed this absolutely. I believed it too, once. And here was uranium quietly, continuously, spontaneously proving this entire worldview wrong. Thorium compounds exhibited the same behavior, which I discovered during my systematic surveys. The radiation of thorium has an intensity of the same order as that of uranium, and it too represents an atomic property of the element. Two completely different elements with different chemical properties, different atomic weights, and different positions in the periodic table both possess this same strange, fundamental property of emitting radiation from within their atoms. A new term became necessary to define this new property of matter manifested by uranium and thorium. I proposed the word radioactivity, and the radioactive elements I called radio elements. The naming captured something essential, because this property proved as fundamental as mass or density belonging to the atom, in a way nothing in chemistry had prepared us to expect. Today, the unit of radioactivity bears my name, the Curie, defined as 37 billion atomic disintegrations per second, roughly the activity of 1 gram of radium-226. When doctors measure radiation doses for cancer patients, when nuclear engineers monitor reactors at facilities from France to Japan, when physicists calibrate instruments in laboratories worldwide, they work in Curies or becquerels, named for Henri. Pitchblendy contains uranium ore, and my measurements of this mineral showed something that should have been impossible. The pitchblende registered more radioactive than pure uranium. Not by a small amount that experimental error might explain, but overwhelmingly, undeniably more active. The measurements were precise, and the conclusion became inescapable. Pitchblende must contain something else, some substance never detected, some element more active than uranium itself, present in quantities so minute that no chemical test had ever revealed it. Greater activity in natural minerals might be determined by the presence of a small quantity of highly radioactive material different from uranium, thorium, and every element known at the time. If this hypothesis held true, ordinary methods of chemical analysis might extract this substance from the mineral. Pierre and I spent years on work that would fundamentally alter our understanding of matter. Tons of pitchblende, literally tons, passed through chemical separations designed to concentrate the unknown radioactive substances. We followed the radioactivity as a hunter follows tracks in snow. Dissolve the pitchblende, separate it into fractions by standard chemical procedures, measure the radioactivity of each fraction. Wherever the radioactivity concentrated, there our unknown element must be hiding. Before our work, chemists discovered elements by their chemical properties, their spectral lines, their reactions with other substances. We discovered elements by their radiation alone, tracking invisible emanations through chemical separations until isolation became possible. This represented an entirely new method of searching for new elements, a method based on radioactivity considered as an atomic property of matter. the first unknown substance concentrated with bismuth during separations, resembling it chemically, co-precipitating with it, forming similar compounds. But its radioactivity was enormous compared to any known substance. 2 new elements emerged from our work, not one. We named the first polonium after my native Poland, then under occupation and erased from maps of Europe. The second we named radium because its radioactivity proved so extraordinarily intense. 5 million times greater, the radioactivity of radium in solid salts compared to an equal weight of uranium. 5 million times. A gram of uranium sits quietly, barely detectable. A gram of radium blazes with invisible fire, pouring out energy at a rate that staggers comprehension. A substance that looks like ordinary white salt sits quietly in a glass tube, obeys all the normal laws of chemistry, forms compounds, dissolves in water, crystallizes out again. And yet this collection of atoms pours out energy at a rate that defies everything scientists had believed about the stability of matter. Radium salts captured the public imagination through another property. They are spontaneously luminous. A pale blue light glows in the dark, visible to the eye even in absolute darkness. This light comes from the radiation itself, exciting the surrounding material and causing fluorescence. A tube of radium in a dark room functions like a tiny self-powered lamp that never dims, requires no fuel, and simply shines on and on through the years. My notebooks from that era still glow faintly. They remain too radioactive to handle without protection and are stored today in lead-lined boxes at the Bibliothèque Nationale de France. Visitors who wish to view them must sign liability waivers acknowledging the risk. About 118 calories per gram of radium per hour, that is the continuous liberation of energy which can be measured as heat. Nothing burns, no chemical reaction occurs. The substance shows no visible consumption. Yet hour after hour, day after day, year after year, the energy flows outward. I could hold a tube of radium and feel it warming my palm with energy drawn from the transformation of atoms. My professors at the Sorbonne would have dismissed any student who suggested energy could materialize from apparently unchanged matter. I would have dismissed that student myself. But radium did not care about our lectures. It simply radiated year after year, making physicists look like fools. The energy must come from somewhere. And this is not philosophy, but the most fundamental law of physics. Energy cannot be created from nothing. We had to choose. Abandon the law of conservation of energy, or accept that atoms contained energy we had never suspected. Both options seemed impossible. Only one was correct. Early investigations troubled us deeply on exactly this question. The constancy of the radiation caused astonishment to physicists who first studied the discovery. Uranium exhibits no appreciable change of state, no visible chemical transformation, and remains, or so it seems, identical with itself. The source of energy which it emits stays undetectable, and therein lies the interest of the phenomenon. Hypotheses multiplied. Unknown external radiation permeating all of space might allow radioactive substances to absorb and re-emit it. Radioactivity might extract energy from surrounding air. The law of conservation of energy might simply fail at the atomic level. But experiments ruled out each possibility. Radioactivity continues undiminished in a vacuum, underground, shielded from cosmic radiation in every environment tested. The energy cannot be coming from outside. Pierre and I put forward our hypothesis. The radiation is an emission of matter accompanied by a loss in weight of the active substances, and the energy is taken from the substance itself, whose evolution is not yet completed, and which undergoes an atomic transformation. An atomic transformation. The atom, which every chemist had learned, was the fundamental, indivisible, unchangeable building block of matter. The atom itself was changing. This was not merely giving off energy like a hot object cooling down. This was restructuring at the deepest level possible. 19th century chemistry called this heresy. The atoms, indivisible from the chemical point of view, are here divisible, and the subatoms are in motion. We were forced to recognize how limited is our direct perception of the world which surrounds us, and how numerous and varied may be the phenomena which we pass without a suspicion of their existence until the day when a fortunate observation reveals them. The materialistic theory of radioactivity leads us to consider that radioactive matter is not in an ordinary chemical state. According to this theory, the atoms do not constitute a stable state, since particles smaller than the atom are emitted. What we witness in radioactivity is nothing less than the spontaneous disintegration of atoms themselves. Consider a single atom of radium, because the abstraction can obscure the wonder. It sits there, apparently unchanged, for perhaps 1,000 years. Then, without any external cause, without any trigger, without any reason that classical physics can explain, something shifts within its interior structure. The atom throws off a particle, what Ernest Rutherford named an alpha particle, and transforms into something else entirely. A different element emerges. Not a different compound, not a different configuration of the same atoms, but a fundamentally different type of matter. 3 different kinds of radiation emerge from radioactive atoms, and the details matter. Alpha rays consist of particles of matter with a positive electric charge, and about 4 times the mass of a hydrogen atom. These particles exit radioactive atoms with tremendous energy, but they lose this energy quickly as they move through matter. A thin sheet of aluminum foil allows an alpha particle to pass through, but anything thicker stops it. Your skin, a sheet of paper, a few centimeters of air, these provide sufficient barriers against alpha rays. Beta rays are also particles, but of a very different character. A beta particle weighs far less and carries a negative electric charge. J. Thomson had just identified this particle in 1897, the year after Becquerel's discovery, calling it the electron. Beta particles travel at nearly the speed of light and penetrate much farther than alpha particles, passing through half a centimeter of aluminum before being stopped. Gamma rays form the 3rd type, and these are not particles at all, but electromagnetic waves, similar to the X-rays that Wilhelm Röntgen had discovered in 1895, just 1 year before Becquerel found radioactivity, but far more energetic. Gamma rays penetrate deeply into matter. A small fraction can pass through even a meter of concrete. This is why the walls surrounding modern nuclear reactors must be so thick, and why the containment failures at Chernobyl in 1986 and Fukushima in 2011 proved so catastrophic. The gamma rays I measured with my piezoelectric quartz electrometer, those same rays, when released in massive quantities from reactor meltdowns, can make entire regions uninhabitable for generations. Every chemistry professor in Europe would have laughed at the alchemists. I did too, once. Their obsession with transmuting lead into gold seemed like medieval superstition, a failure to understand that chemical reactions rearrange atoms but do not change them. A gold atom that enters a reaction emerges as a gold atom. Transmutation was impossible, we were certain, but here was uranium, quietly transmuting itself into thorium, then into radium, then into radon, then onward through a chain of transformations no alchemist ever imagined. The alchemists were right about the fundamental possibility. They were merely wrong about the method. We were not laughing anymore. We were taking notes. Mathematical precision governs this process. Each radioactive isotope has what we call a half-life, a characteristic time in which half of any given sample will decay. Approximately 1,600 years marks the half-life of radium, which means a gram of radium today becomes half a gram in 1,600 years, then a quarter gram in another 1,600 years, and so on, diminishing but never quite reaching zero. The mathematics of radioactive decay, exponential functions governed by probability, would later prove identical to equations governing phenomena no one connected to nuclear physics. insurance actuaries calculating life expectancy, epidemiologists modeling how diseases spread through populations, economists tracking currency depreciation, even the carbon 14 dating that lets archaeologists determine the age of ancient artifacts, all use the same mathematics I applied to counting atomic disintegrations in my laboratory. The universe has a limited vocabulary for describing gradual change, and radioactive decay taught us to read it. This half-life remains absolutely constant for any given radioactive substance. Heat or cold cannot alter it, nor can pressure or vacuum, nor chemical combination or electrical fields. Unlike human calendars, which are arbitrary divisions that politicians adjust for convenience, half-life answers only to nuclear forces. 1,600 years for radium. Not negotiable, not adjustable. The same in Paris, in the depths of the ocean, at the edge of the solar system. Different radioactive substances have wildly different half-lives, with some decaying in fractions of a second while others endure for billions of years. About 4.5 billion years marks the half-life of uranium-238, which explains why it appears so stable in comparison. Its atoms decay so slowly that watching a sample for a human lifetime would reveal no noticeable change. Yet the decay continues atom by atom across geological ages. The uranium that exists on Earth today has been decaying since before our planet formed, and most of it still remains. That slow decay generates heat. Uranium and thorium in Earth's mantle have been releasing energy for 4.5 billion years, and that energy is why our planet's core remains molten. Plate tectonics, volcanoes, the magnetic field that shields us from solar radiation, the very habitability of Earth, all are powered by radioactivity. Without uranium and thorium generating heat in the deep Earth, our planet would have frozen solid billions of years ago, a dead rock like Mars. Only 138 days marks the half-life of the longest-lived polonium isotope, which is startlingly brief. This short half-life helps explain why isolating polonium in pure form proved impossible for me. Even as I performed meticulous fractional crystallizations, the polonium in my raw material was disappearing, transmuting into other elements through rapid radioactive decay. I was chasing a target that was constantly vanishing. But here is the beautiful complexity. Radium does not simply vanish when it decays. It transforms into another element which is itself radioactive. This daughter element decays into yet another, which decays again, creating a chain of transformations. The radium in pitchblende is itself a descendant of uranium, created through this long chain of nuclear alchemy. This explains something that puzzled me for years. Radium is found in uranium ores, but never by itself, because radium is constantly being created by the decay of uranium and constantly decaying itself into something else. It exists in a kind of equilibrium maintained by the slow drip of uranium decay above it in the chain. The equilibrium is precise enough that geologists can now use the ratios of uranium to its decay products to date rocks that are billions of years old, reading Earth's history in the patient accumulation of atomic transformations. People asked me whether I was afraid, working with substances that burned my skin, that made my notebooks too radioactive to handle safely for decades after my death. Afraid? Fear is a response to the unknown. I made the unknown known. What remained to fear? Radioactive materials require caution, yes. When one studies strongly radioactive substances, special precautions must be taken. Various objects used in a laboratory where such work is done become radioactive in a short time and act upon photographic plates through black paper. The rays have physiological effects. Pierre and I experienced them ourselves, with skin becoming inflamed and sore where exposure was prolonged. The tips of my fingers were perpetually cracked and painful, and Pierre carried radium samples in his pocket to demonstrate their properties, developing sores that would not heal. But consider what this property of matter makes possible. Radiation from radioactive elements can penetrate matter that stops ordinary light completely. This property proved invaluable in ways no one anticipated when the discovery was first made. A photograph can be made through opaque materials. Bones can be seen through flesh. The internal structure of the body, previously accessible only through surgery, becomes visible to the trained observer. Wounded soldiers arriving at field hospitals during the war carried bullets and shrapnel buried deep in their bodies, and I recognized that this technology could save lives on a massive scale. Without knowing exactly where these fragments lay, surgeons had to probe blindly, causing additional damage, wasting precious time, often failing to locate the metal at all. Men died or lost limbs because of this uncertainty. Mobile radiological units, which the soldiers came to call petites curies, used X-ray equipment powered by generators mounted in automobiles. These units could reach field hospitals near the front lines where the wounded were being treated. With radiological imaging, a surgeon could see precisely where a bullet had lodged, plot the safest path to extract it, and proceed with confidence rather than guesswork. Training operators, securing equipment, raising funds, driving the vehicles myself when necessary, the effort was immense. I taught my daughter Irene, then just 17 years old, to operate the equipment, and she served alongside me at the front. By the end of the war, nearly 200 mobile units and over 100 fixed radiological installations operated in France alone. An estimated 1 million wounded soldiers were examined using this technology. When radium was discovered, no one knew it would prove useful in hospitals. The work was one of pure science. We did not set out to save soldiers' lives or to treat cancer. We set out to understand the nature of matter. The applications followed from the understanding. Radium itself, not just X-rays produced by electrical equipment, but the radiation from radium, has shown therapeutic effects against certain diseases. The radiation can destroy diseased tissue more readily than healthy tissue in some circumstances, and this property has been used to treat cancers and other conditions that were previously untreatable. Today, the Institute Curie, which I founded in Paris and which continues to operate more than a century later, remains one of the world's leading centers for cancer treatment using radiation. Radiation oncology, nuclear medicine, PET scans that reveal tumors invisible to other imaging, all descend from the fundamental discovery that atoms can be unstable, can release energy, can transform. The energy released by radioactive decay suggests possibilities that stagger the imagination, despite being dangerous in excessive exposure. If atoms can release such enormous quantities of energy through spontaneous transformation, might this energy be harnessed at scale? A single gram of radium, through its complete decay chain, releases more energy than burning tons of coal. I did not live to see nuclear power plants or nuclear weapons. I died in 1934. My bone marrow destroyed by decades of radiation exposure, 11 years before the bombs fell on Hiroshima and Nagasaki. My work made those weapons possible. It also made nuclear power possible, and radiation therapy for cancer, and smoke detectors in every home, and the nuclear batteries that power spacecraft exploring the outer solar system. The science is pure. What humanity chooses to do with it reflects humanity, not the science. Irene and her husband, Frédéric Joliot, continued the research after my death, discovering artificial radioactivity, the ability to make ordinary stable elements radioactive through bombardment with particles. They received their own Nobel Prize for this work in 1935, the year after I died. The Curie family has now received 5 Nobel Prizes across 2 generations. But the prizes matter less than what they represent. The gradual uncovering of nature's deepest structure, one careful measurement at a time. Beyond all practical applications, radioactivity teaches a deeper truth. The universe contains far more than we can directly perceive. Before 1896, no one suspected that certain atoms were constantly, silently transforming themselves and releasing energy. This process had been occurring since the formation of the Earth, and indeed since the formation of the elements in dying stars, yet it was invisible to human senses and undetectable by human instruments until the right questions were asked. What else might be occurring all around us at this very moment that we lack the instruments to detect or the concepts to imagine? Radioactivity adds a new group to the great number of invisible radiations now known. Once more, we are forced to recognize how limited is our direct perception of the world which surrounds us, and how numerous and varied may be the phenomena which we pass without a suspicion of their existence. The radiations longest known to us are those capable of acting directly upon our senses, the rays of visible light, the vibrations of sound. But beyond these lie vast territories of invisible radiation. Infrared rays, which we feel as heat, ultraviolet rays, which tan the skin but which the eye cannot see, X-rays, which pass through flesh and reveal bone, radio waves, which traverse space without visible sign, and now radioactivity, emanations that require no external energy source, that pour continuously from certain atoms as they transform themselves. Each discovery of a new form of radiation has expanded our understanding of the universe. Each has reminded us that what we perceive directly represents only a tiny fraction of what exists. Cosmic rays from distant stars stream through your body continuously, right now. Radioactive potassium 40 inches your own bones emits particles that have done so since before you were born. Approximately 7,000 becquerels of activity, making you measurably radioactive at this very moment. Radon gas, a daughter of uranium decay, rises from the soil and enters your lungs with every breath. The granite in buildings, the concrete in sidewalks, even the bananas you eat, all contain radioactive isotopes undergoing their slow, inexorable transformation. You have lived your entire life bathed in radioactivity without ever knowing it. The levels are almost always far too low to cause harm, so this is not cause for alarm. But the conceptual shift is enormous. Matter itself is not the stable, solid, permanent thing that intuition suggests. At the atomic level, the universe is in constant flux. Atoms transform. Energy flows, and the elements themselves are merely temporary configurations in an endless dance of nuclear chain. Radioactive decay is also one of nature's only truly random processes, quantum randomness that cannot be predicted even in principle. You can say that half of a sample of radium will decay in 1,600 years, but you cannot say which atoms will decay or when. Each decay is a genuinely random event, an irreducible unpredictability built into the fabric of reality. Einstein found this disturbing. He famously objected that God does not play dice with the universe. But the universe plays dice whether Einstein approved or not, and the randomness of radioactive decay is now harvested for cryptographic systems that protect your banking information and secure communications worldwide. Radioactivity chemistry differs from any chemistry that came before. In this new science, the electrometer serves as the current tool rather than the balance. We deal currently in the laboratory with substances whose presence is only shown to us by their radioactive properties, but which we can nevertheless determine, dissolve, reprecipitate from their solutions, and deposit electrolytically. This is an entirely separate kind of chemistry, one that might well be called the chemistry of the imponderable. Measuring what cannot be seen, detecting what cannot be felt, quantifying what cannot be weighed by ordinary means, this work occupied my life. The way of progress is neither swift nor easy. 40 years of research, 4 years to isolate 1/10 of a gram of radium chloride, years more to isolate pure metallic radium. But the rewards, not personal rewards, but rewards for human knowledge, proved immeasurable. My doctoral thesis raised a question that still echoes. Is atomic radioactivity a general phenomenon? I undertook research with the idea that it was scarcely probable that radioactivity, considered as an atomic property, should belong to a certain kind of matter to the exclusion of all other. If radioactivity truly represents a fundamental property of atoms, should not all atoms possess it to some degree? Experiments at that time found no evidence of radioactivity in most elements. Uranium, thorium, and their families seem to stand alone, but this apparent isolation has proven less absolute than it once appeared. Certain isotopes of many elements are now known to be radioactive, including potassium, carbon, rubidium, and others that no one suspected. The periodic table contains far more radioactive species than were known in my early investigations. Questions remain about why some atoms stay stable and others radioactive, about what determines whether a nucleus will persist unchanged for billions of years or decay in a fraction of a second. These questions reach toward the deepest structure of matter, toward forces and configurations we were only beginning to understand in my time, and which physicists continue to explore today. Radioactivity deserves different thinking than what most people bring to it. Do not treat it as a strange anomaly, a dangerous curiosity, an exception to the rules of nature. Treat it as a window into the true structure of matter. Treat it as evidence that atoms are not the ultimate building blocks, but are themselves complex systems with internal structure and stored energy. Treat it as proof that the universe is far stranger, far more dynamic, far more wonderful than unaided senses can reveal. The atom is not unchanging and indivisible since its particles are radiated out. Radioactive matter is subject to transformation, and that very transformation is the source of the energy in radiation. But this is not a usual chemical transformation, for here the atom itself is subject to change. If radioactivity is a result of transformation of matter, then the atom must transform, as radioactivity is an atomic phenomenon. Most people see the danger and miss the revelation. They notice the practical applications and overlook the deeper implications. They learn the facts and fail to grasp the meaning. Radioactivity tells us that matter is not what we thought it was. Energy is not what we thought it was. Stability is an illusion measured against human timescales. At the deepest level, reality is a process of continuous transformation. Uranium exhibits no appreciable change of state, no visible chemical transformation. It remains, or so it seems, identical with itself, the source of energy which it emits undetectable. And therein lies the interest of the phenomenon. That is the truth of radioactivity. Not a hazard to be managed or a tool to be exploited, though it is both of those things, but a fundamental fact about the universe that demands reconsideration of everything we thought we knew about the nature of matter. I was the first woman to win a Nobel Prize, the first person to win Nobel Prizes in 2 different sciences, the first female professor at the Sorbonne, where I lectured in the same halls where I had once been forbidden to enroll as a student from occupied Poland. None of that matters as much as the science itself. In science, we must be interested in things, not in persons. I have told you what I have observed, what I have measured, what I have concluded, and the work speaks for itself. The mystery of radioactivity first appeared as a puzzle in a photographic plate darkened by uranium salts in Becquerel's laboratory. From that small observation has grown a new understanding of matter itself. This is always how science progresses. From tiny anomalies carefully pursued to revolutionary transformations in human knowledge. One never notices what has been done. One can only see what remains to be done. And in the study of radioactivity, what remains is vast. A new science barely begun, a new understanding of matter still taking shape, new applications and new dangers and new wonders waiting to be discovered by those who come after. That is what radioactivity really is. Not merely a hazard, not merely a technology, not merely an energy source. It is a revelation about the impermanence of matter, the hidden dynamism of atoms, and the endless capacity of nature to surprise those who have the patience and precision to observe carefully. The universe is far stranger than we imagine, and radioactivity was merely the first proof